Now we are in a good position to formulate and analyze our first algorithm to solve large-scale optimization problems. The algorithm is called the subgradient method. And it is very analogous to the so-called gradient method, where you take, in each iteration, a step into the opposite direction to the gradient. And since for the gradient method, the function is differentiable, and the gradient gives you the direction of the steepest ascent, minus the gradient will give you the direction of the steepest descent. And things are still a bit different in the subgradient method, but formally the algorithms look very similar. Okay, so let's first fix the general setting. We want to minimize a proper convex function f mapping from H not to R bar, sorry, just to R. And the reason is that we want to find at each step a subgradient, and we need to make sure that such a subgradient exists. Otherwise, your algorithm might just die because there is no way to proceed. So since we have seen that any convex proper function has a subgradient, so the subdifferential is not empty, at each interior point of its domain, if we make the domain the whole space H, then the subdifferential at each point will be non-empty, so there will be a subgradient to evaluate. And therefore we set R as the target for our function. There are algorithms for constraint optimization problems where you have where you want to restrict yourself to a convex set, and you will analyze this algorithm as an exercise. Okay. Yeah. Here in the proof we will, or in the analysis, we will make use of the fact that H is still a finite dimensional inner product space. Okay, now let's formulate the algorithm. The algorithm goes as follows. So start with some x0 in H, and then for each iteration, I will denote the iteration number by 0, so that we can just name our things. What are we doing? So we want to take our point xn, and what we want is we take in the gradient method we would take a gradient. For the subgradient method we can take a subgradient. So choose Sn in df of xn. Then so this gives us our direction. So then we want to choose a step length. I call it gamma n greater than 0. Of course, this may in some way depend on Sn or on xn or whatever you know about your function. And then we set our next iteration point as the old one minus the step length times the subgradient. Okay, and this will generate a sequence going from x0. It will generate S0, gamma 0, x1 and s1 gamma 1 x2 and so on. So this is a proper algorithm, and our considerations show that we can choose an Sn in this non-empty subdifferential, so this is well defined. Okay, some remarks. So it's not necessary to know the whole subdifferential here. It's only necessary to know one subgradient. So in general, this choice here is not unique. Starting from points x0, you can generate, you might be able to generate several sequences which all satisfy this algorithm. So in some definitions, maybe this is not a real algorithm, but so you can take any like choice function which gives you a subgradient, some subgradient from a point, and then you can see this as a well-defined algorithm. Okay. Now I want to give you some demotivating examples which should show how the subgradient methods is set apart from the gradient method. So the first example shows that minus Sn is in general not a direction of descent. This is important. So for the gradient method, minus the gradient will always be the direction of the steepest descent. So if you choose your step length gamma n small enough, you will always get some descent because you have this approximation, this first order approximation. For the subgradient method, you only have some sublinear approximation, and it will not guarantee that minus Sn is gives you any descent. It can even go upwards, and no matter how you choose the step size. And the example we will have a look at is f is a function defined on R2 with values in R, and we will set this f of x1, x2 is, just for safety, alpha times x1 plus beta times norm of so absolute value of x1 plus beta times absolute value of x2 for some alpha beta greater than 0. Then this is obviously a convex function. So we can calculate the subdifferential. Let's just see. So the subdifferential, the points where this is non-differentiable will be along these axes. So the level sets will look like these whatever these shapes are called. So the points of non-differentiability will be like this, and you have these level sets here. So any subgradient here would point into this direction. So this would be something like, if this is xn, then this is Sn, and here you have the whole thing here, so these would be possible values of xn if you're in this point here. Okay, and let's calculate the concrete subdifferential for the point 0, 1. Okay, so assume that xn would be 0, 1, and we want to find all the possible values for Sn, and then pick the worst one, because this is meant to be a demotivating example which shows you some rather negative statement. So at 0, 1, we have here for a point of non-differentiability for x1, and the subdifferential of the absolute value function at x1 will be the closed interval from -1 to 1. If you multiply this with alpha, then you get the closed interval from minus alpha to alpha. And the second part is not really affected by any change in x1. So you get the closed interval minus alpha alpha. And for the second component, you just have a positive value here. So this is differentiable with respect to x2, and the derivative will be 1. And since you multiply this with beta, then the derivative will be just beta. So this is the set of all pairs where the first component is between minus alpha and alpha, and the second component is exactly equal to beta. Okay. So then our algorithm would choose some subgradient. I leave out the iteration number here. So here, this is the point 0, 1, and now we take a subgradient. So for example, we can choose not a set, of course, just an element of the set. So we can choose alpha, beta. So alpha here, beta here, and this is in the subdifferential of 0, 1. And now we want to calculate the f at the point like xn 0, 1 minus gamma times the this subgradient here, and want to compare it with f at 0, 1. Okay, what do we get? So we get f at 0 minus gamma a. So we have minus, oh sorry, not so we have f at 0 minus gamma a, 1 minus gamma 0 minus gamma alpha, 1 minus gamma beta. So you have alpha absolute value of 0 minus gamma alpha plus beta absolute value of 1 minus gamma beta. And of course, you want to have gamma a positive step size or step length. Okay, and alpha and beta are also positive. Okay, so you have the absolute value of minus gamma alpha. Since all of these are positive, only the minus remains, so the absolute value is just gamma alpha squared. And then you can distinguish two cases. The first case is that gamma is small enough so that this absolute value is positive. So then this will be beta 1 minus gamma beta for gamma between 0 and 1 over beta, I guess. Yeah, looks right. And otherwise you have beta times gamma beta minus 1. And this is for whenever beta is larger than 1 over beta. And these values are obviously equal to 0 in the case that gamma is equal to 1 over beta. So in both cases, so this statement is true for both cases. Okay, and just to put everything in one formula, you have, sorry, I forgot f of 0, 1, of course. Okay. So f of 0, 1 is also missing here, by the way. So f of 0, 1 is just alpha times 0 plus beta times 1. So this is minus beta. Okay. And this is just... so in the first case, you just have beta here. So this is just gamma alpha square minus gamma beta square. So this is gamma alpha square minus beta square. Okay. And in the second case, you have gamma alpha square plus gamma beta square minus beta minus beta, so minus 2 beta. So this is for the case gamma between 0 and 1 over beta, and this is the case gamma greater or equal than 1 over beta. Okay, so this is... So we are actually mainly interested in the case for rather small step sizes gamma. So mainly in the first case. So this here will be greater than 0 for alpha greater than beta. This means if in our harmless looking objective function alpha is greater than beta, for example, alpha is equal to 2, beta is equal to 1 for some reason, then this will be a subgradient, and the minus the subgradient is not the direction of descent. So no matter how small you choose the step size, you always get an ascent, strict ascent. So you will your function value at the next iteration will be higher than the function value at the previous iteration. And this is meant by minus Sn is in general not a direction of descent. Okay, so this was the first demotivating example. Now the next demotivating example, why you need to be careful and why our analysis is important. So the second, wisdom which you should take away from the example is constant step sizes or step lengths gamma n just equal to gamma for all n will not guarantee convergence to a solution. Okay. The example is simpler. So you just take a one-dimensional function equal to the absolute value. You start with x. You take some gamma greater than 0. According to this, you start with x0 equals a quarter of gamma. Then the subdifferential here, so this is x0. Subdifferential will be minus 1. Will be 1, and minus the subdifferential will be minus 1. So you go into the negative direction with a step length of gamma. So you end up somewhere here at minus 3/4 of gamma. And you get to a point where you have the step length, where you also have the minus 1 as a subgradient. So you would take a step with length gamma back to the positive side. So you get back to 1/4 of gamma. X3 equals minus 3/4 gamma, etc. So this does not converge to 0, which is the unique minimum of this function. So it does not converge to 0, Nor, for example, does sometimes you have, as we also will see, sometimes some average of these points converges to a solution and not the iteration sequence itself, for example. But here in this case, you see the average converges obviously to minus a quarter of gamma, which is also not the solution. So does not converge to 0, nor does the average of, so like the average of this would be just 1/4 of gamma, the average of this would be, minus a quarter of gamma, and then, you sum up, divide by 3, this would be the next point, then you sum up all these values, divide by 4, so that you are back to minus 1/4 of gamma, and so on. So even the sequence of averages neither does, actually the sequence of average, but the average of these points. So we have to, in one way or the other, like do something with our step sizes and let them converge to 0. And we will see in the next video, first of all, why, and second, how we do that in order to get a meaningful result which guarantees the convergence to some solution.